Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good evening. So today we continue to our next subtopic, graph representation. It can be present in adjacency list, adjacency matrix, and incident matrices. So first is the definition of the adjacency list. So an adjacency list can be used to represent a graph with no multiple edges by specifying the vertices that are adjacent to each vertex of the graph. So the very first thing that you have to see before you can declare whether that adjacent whether that vertex is the adjacent vertex to that particular vertex, you must to ensure the edge is there. Oh, wow. So like in this case, you can see that A has vertex A has edge from A to B, and A has edge from A to C, and A has edge from A to E. So in this case, we can say that B, C, and E are the adjacent vertices for A. Whereas for B here, you can see that B only has one edge, which from B to A. So we can say that for B, it only has one vertex, which is an A. So for the directed graph, to declare whether the next vertex is adjacent or not, you have to see the out degree point here. So you can say that now for the vertex A, it's going out to B, and A is going out to C, and A is going out to D, and A is going out to E. So we say that B, C, D, and E are the terminal or adjacent vertices to an A. For the B, you can see that B is going out to D, and B going out to itself. So there are two terminal vertices for B, which are B and D. And you can see, okay, for the D here there is no outgoing edge from D, so D doesn't has any adjacent. All right. For the adjacency matrices, this actually you have seen this in our previous lecture. So suppose that G is presented in vertex and edge. It's a simple graph where the number of V is equal to N. Arbitrarily list the vertices of G as V1, V2 until Vn. The adjacency matrix it present in AG of G, which with respect to the listing of vertices is the n by n 0, 1 matrix with 1 as its ij entry when Vi and Vj are adjacent, and 0 when they are not adjacent. So in terms of matrix, you can present the adjacency vertices by having 0, 1 matrix if there are if the adjacency happen, then we say it as 1. If the adjacency doesn't happen, then we will declare it as 0. So this is the simplified way of these words. Aij is equal to 1 if Vij is an edge of G, and 0 is otherwise. So this is the example. So now in this case, you can have this. We can say that this is the A, this is the vertex for the B, this is for C, this is for D, and same goes to the rows. This is A, this is B, this is C, and this is D. Alright, so now we check for the A, for the vertex A to vertex A, is there any loop here? No, right? So that's why it is 0. What about for the vertex B? Is there any B to A? B to A? Yes, it has. So 1. What about C? C to A, it has. So we say it as 1. D to A, is there any line from D to A? Any edge from D to A? Yes, 1. What about, okay, now we see again from A to B has 1. B, it doesn't has loop, so 0. What about C to B? C to B, yes, it has 1. What about D? B to D. B to D, no, so we say as 0. So, alright, this is the two examples you can see here. Alright, for the adjacency matrices, can be used to represent graph with loops and multiple edges. And this one, it can be used to represent loops and multiple edges. A loop at the vertex vi is represented by a 1 at the ij position of the matrix. When multiple edges connect the same pair of vertices vi and vj, the I and j entry equals the number of edges connecting the pair of vertices. Okay, you see in this part, you can, this is vertex A, B, C, and D. Same goes to in the rows A, B, C. Alright, so in this case, you can see there is no loop for the AA, so it is 0. What about B to A? B to A has 3 edge, 1, 2, and 3. So we declare it as 3. What about C to A? C to A, nothing, 0. What about D to A? D to A, it has 2 edges. So we write it as 2. What about A to B here? Again, it is 3. B to B, there is no loop here, 0. C to B, 1. D to B, has 1. What about C? C, nothing, 0. CB, it has 1. CC, 1. CC, because there is a loop here. And then CD, 2. Right, and you can check for the D as well. Right. Adjacency matrix in terms of directed graph. Consider directed graph. The matrix for a directed graph G equal to VE has a 1 in its ij position if there is an edge from Vi to Vj, where Vi, V2, Vn is a list of the vertices. In other words, if the graph adjacency matrix is Ag equal to Aij, then the Aij is equal to 1 if Vi, Vj is an edge of G, 0 is otherwise. The adjacency matrix does not have to be symmetric because there may not be an edge from Vi to Vj when there is an edge from Vj to Vi. The represent directed matrix graph, the value of Aij is the number of edges connecting Vi to Vj. Same as before. Let G, this is what we call as incidence matrices. Let G equal to VE is an undirected graph with vertices where V1, V2, Vn and edges E1, E2 until Em. The incident matrix with respect to the ordering of V and E is the N multiplied by M, matrix M equal to Mij. Mij equal to 1 when Hej is incident with Vi. 0 is otherwise. So in this case, you can see here, the rows going from top to bottom represent the V. So this one V1, this one is V2, this one is V3, this one is V4, this one is V5. And the column present the edges, E1, E2, E3, E4, E5, and E6. Alright, so in this case, you can check, you can find the E1 from this figure. So E1, where is E1? E1 is here. Alright, and E1 connect V1 to V4, right? So the E1 incident to V1. So that's why we write, since the incidents happen, so we declare it as 1. What about E2? E2, where is E2? Okay, E2 connect V1 to V5. So we say that E2 incident with V1, 1. What about E3? Where is E3? Alright, E3 connect V4 to V2. And since that E3 doesn't connect V1 to anything, to any vertex, so we declare it as 0. Same goes to E4, E5, E6. And you can check for the rest. This is for the case of simple graph. So what about pseudo graph? What about to pseudo graph? So same for the rows here, it is V1, okay, and V2, V3, V4, V5. And for the age, it is E1, E2, E3, E4, E5, E6, E7, E8. Alright, so now we check for the E1. E1, where is E1? Okay, E1 is a loop from V1 to V1. So that's why we say as 1. So what about E2? Let's check for the E2. Where is E2? E2 here. E2 connect V1 to V2. So there is an incidence between E1 and V1. So that's why we put it as here 1. What about we check E5 here? Right, where is E5? E5 connect V3 to V5. And since E5 doesn't connect V1 to any vertex, so we declare as 0. Right? Alright, for the Euler and Hamiltonian graphs, I will put another video for this. Alright, thank you.